All right, so this chapter deals with thermodynamic properties. There's one chapter that's critical. It looks easy. A lot of students yawn, oh, this is so trivial. But it's not trivial. It's really foundational. And a lot of times I'll get asked questions, and in Thermo 2, like, Professor, I don't understand this. And really, they're lacking a good, firm grasp of something out of chapter 3, out of thermodynamic properties. So there's a lot to cover. Let's just jump into it. So first of all, the state principle. We were already introduced to the state principle. It's one of the most important foundations that allow us to make a lot of property evaluations. So what is the state principle? It says for any two independent intensive thermodynamic properties, that fixes the thermodynamic state of the pure, simple, compressible substance. And because it fixes the state, it allows one, like us, if we know two independent intensive properties, to go and get a whole pile of other intensive properties. So a couple questions. What's an intensive property? Well, something that doesn't depend on the size or the extent or the mass of the system. Good example of intensive property is temperature intensive. Well, you take the system, you think about it has a temperature, cut it in half, and now is each side value half of what it was before? That's the easy test. So if it's 50 degrees C for the whole thing, you cut it in half. Is each part 25 degrees C and 25 degrees C? No. So temperature is intensive. How about pressure? Intensive. How about specific internal energy, U? It's not cap U. It's lowercase u. It's not just the internal energy. It's the specific internal energy, which is related to cap U by defined as cap U divided by M. So is the specific internal energy intensive? How about the specific volume? Now you're never going to answer another question because you got one wrong. The specific volume, the cap V volume, the specific volume, which is defined as the volume, sometimes I put that for so it's different than velocity, divided by mass. How about density? Density is the reciprocal of specific volume. Let's say water, I have a jug of water, and I say the density of the water is 1,000, liquid water, 1,000 kilograms per cubic meter. I cut it in half. Is the density of the top half 500 and the bottom half 500 kilograms per cubic meter, or is the density of the top half 1,000, the bottom half 1,000? So what about density? It's intensive. The reciprocal of density, specific volume, intensive. We're going to get to internal, well, we already did internal energy. We'll get another property, H. You can have cap H, or you can have lowercase h. What do you think the connotation is? One is per unit mass. One is specific enthalpy. We're going to have entropy, specific entropy. Intensive, extensive. Intensive, extensive. Intensive, extensive. Intensive, extensive. Okay, so we got it straight. What is an intensive property? There's a lot of intensive properties that we deal with. Okay. What does independent mean? Just like it says, it's independent. If it's dependent, then we have to worry about it. And what we're going to find is that this comes into play right here. Sometimes temperature's not independent of pressure. Sometimes pressure's not independent of temperature. They're linked together. They're not independent in certain cases. In a lot of other cases, they are independent. What does pure, simple, compressible? Well, negligible surface tension effects, negligible magnetic or some other, electronic effects. It's just a very simple compressible substance. What are the list of simple compressible substances we deal with? How about water? Good idea. Water's a great one. So how about any of the refrigerants like 134A and 410A and old ones like 12 and 22? Yes, they're pure, simple, compressible systems. How about oxygen and nitrogen and diatomic air, just air like we're breathing, water vapor, H2O? Yes. A lot of the substances, ammonia, propane, are those types of substances. What happens, you start mixing stuff and things get a little different, and then this state principle is expanded. That's the end of Thermo 2. If you want, flip to the last chapter of the textbook and you'll see more generalized when you put mixtures together. Let's say you put ammonia, NH3, and water, H2O, together, and it's a two-phase mixture of both liquid and vapor. Not so easy. This is, you have to generalize the state principle, and it's not two independent intensive properties fix the state, but you need three and other times more. So what are some examples of the utility of this? Not that surprising. If you're given two independent intensive properties and you want to get another one, that's the name of this chapter. That's the game of this chapter. So maybe you're given temperature and pressure. Can you get internal energy? Maybe you're given temperature and pressure. Can you get volume, specific volume? Can you get the enthalpy, the entropy? All of those are intensive per unit mass. Or switch it around and the game goes on. Given internal energy and pressure, can you get temperature? Given specific volume and pressure, can you get temperature? Given these two, can you get pressure? As long as they're independent and intensive, and you're interested in another intensive property, you should be able to do it. This appendix, which you'll need for the next exam, helps you do it. But sometimes it's a little tricky because a lot of times we like to think of the temperature and the pressure are inputs. Get everything else. That's kind of the way we think. That's the way the table's set up. But it's not really set up if, enthalpy and pressure. You got to think a little bit. I'm given enthalpy and pressure and I want temperature, or enthalpy and pressure and I want internal energy. That's tricky. But theoretically, it's doable, and in computer programs, they've thought about it, implemented root finding algorithms and other ways to make those calculations. Behind the scenes, make it look too easy. All right, so that's our state principle. Air consists of a mixture of primarily oxygen and nitrogen. You'd say maybe this is 79% nitrogen, 21% oxygen. It's at this temperature and pressure. Can it be treated as a pure substance? At first you might say, no, it's not pure oxygen, it's not pure nitrogen. But if you have a container of it, and you go and draw a sample anywhere in the container, is it going to be the same makeup? And if the answer to that is yes, then it's pure. You can treat it as pure. So even a mixture sometimes you can treat as pure substance. What would not be a good example of that? Well, I have to go back to the, you have liquid water. And because you have liquid water in a container, you may have some water vapor in the container, but not much. But let's say you had a mixture of the water with the ammonia, NH3. Well, the ammonia, depending on how cold or hot the water is, likes to be absorbed into the water, and so you'll have liquid water with NH3 in the liquid phase, and then over here you'll have NH3 in the vapor phase. But if I go and draw a sample up here in the vapor, and I go and draw a sample down there in the liquid, the composition is not the same. Over here in this example, the composition will be 2179, no matter where I draw the sample. This example, no. So a mixture of ammonia and water would not be treated as a pure substance. You won't have two independent intensive properties, fixed state, blah, blah, blah. Phases. You've known this for a long time. That's why students say, oh, this chapter is easy. What type of phases do we have? We have the solid, liquid, vapor. I think you all have a lot of experience with solids, liquids, vapors. Is there a fourth phase? What phase is the fourth phase? Plasma? We're not going to do plasma in this class. So let's exclude plasma. Any other fourth phase that you might encounter in many engineering applications, refrigeration application, your internal combustion engines running. We're going to study the flow and energy. You're burning something of fuel to make power, right? Subject of analysis, Otto cycle, diesel cycle, how a jet engine works with the Brayton cycle, vapor power to make electricity by burning coal. Those are the focus of the study of this class. Any other phases other than solid, liquid, vapor? We don't have very many plasmas, so we're going to leave plasma off. Nope. I'm sorry. Well, we'll have mixtures of them, that's right. But these will be the three phases. There's no fourth. All right. So if you look for a fourth or fifth phase in this handbook, in this textbook, you won't find it. Now, can the substances change phase? Can you go from a solid to a solid to a vapor, a liquid to a solid, liquid to a vapor, and back and forth? Sure. How about this one? What do you call that phase change when you're going from solid to a liquid? What do you call that? Solid to a liquid? Melting. Melting. All right. Then what do you think the next one is? What do you call a liquid to a solid? Freezing or solidification, something like that, right? How about vapor to a liquid? Condensation, condensing. How about liquid to the vapor? Opposite of condensation is vaporization, boiling. Evaporation, different terms for different, do you have like air in the presence of it? You might call it evaporation. Boiling, evaporation. Vapor to a solid. Oh, now you're stressing me, Professor. Vapor, do we have any vapor to solid applications? It's okay. Solid to a vapor. You want to do that one first, right? So what is solid to a vapor? Sublimation. Sublimation. Now, how about this solid to a vapor? Do we ever see that everywhere, anywhere in my everyday presence? Your experience in your 20-some years of life on this earth. Dry ice is a great example. So I have something really cold. It's frozen ice. Don't touch it. It's super cold, right? You want to put it somewhere and keep something really cold, but it's going to eventually go, all of it will start in a solid phase, and it won't go to liquid. It'll go from solid straight into vapor. Dry ice does that. CO2. You ever use dry ice, and then you say, where's the puddle of melted CO2? Like you put in ice into a cooler, solid water, and then after a long time, you open up the cooler, you have a bag of water. It went from solid to liquid, but not the dry ice. You won't find a liquid puddle of CO2 in there. How about another example? How many people ever cracked ice cube trays out of their freezer? How many people said, oh, the ice cube tray's been in there for a month? And they pull it out, or 2 months, they pull it out, and they look at the ice cubes in the tray. It didn't just overnight. Overnight versus 2 months it's sitting in the freezer. What do you notice about that ice cube tray? sitting there for 2 months. It's like, hey, who stole some of this ice? Isn't it gone? Where did it go? Did it melt and then liquid flow out of the system? No. It actually solidified. It's ice. It's solid ice. But your refrigerator is working to keep it defrosted. And so it's always pulling humidity out. Anybody had a not frost-free or defrost type of freezer? You ever open it up and it slowly, is a cavern of built-in ice? And then you have to defrost. This is old school. But when I was very young, a lot of them were still that way. Where you had to manually unplug it, let it defrost that way. Okay, or get in there and chip it, knock it off so you could get it defrosted quicker. But anyway, ice cubes left in a freezer will undergo a solid to vapor and then be out of the system. The last one, let's try and figure a name for that one. Vapor to solid. Pardon? The opposite of sublimation. Sublimation is solid to vapor. Just like one was boiling, one was condensing, vaporization, condensing. Anyway, this is like a deposition. A vapor to a solid is a deposition. Yeah, there's some engineering applications of that. What do we study a lot in this class for power cycles and traditional thermodynamics? We study this one again and again and again. In your refrigeration cycle, what's keeping this building cool in the middle of the summer? There's a lot of fluid refrigerant that's changing phase repeatedly. It's going in one device, condensing, going in another device, evaporating. One device is called the condenser, one is the evaporator. Take a look at power plants. Power plants run by boiling water, throwing it through a steam turbine. Then they condense it in the condenser, put a pump, back to the boiler. So we're changing phase of water and refrigerants all the time in many engineering applications. Is it possible to have a mixture of some liquid and some vapor in thermal equilibrium and mechanical equilibrium at the same time in a system? Yep. So we can have our single phases and then we can have mixtures of two phases in thermal mechanical equilibrium. So that's definitely true. How many people have seen an illustration like this somewhere in their prior life? Yeah, this is a PVT surface or a PVT solid. Words make a difference. Is this a PVT surface or a PVT solid? It's a surface. So if you're plotting a surface in 3D, isn't this 3 dimensions? What are the 3 dimensions? Pressure, volume, and temperature. So let's take a look at this. Where is the temperature axis? Here. Where is the volume axis? Here. But notice it's a lowercase v, it's a specific volume. And what about the pressure axis? Here. True? And so they're going to show us a surface in 3D. But let's get the axes down first. For the temperature axis, which direction is the direction of increasing temperature? Is this the direction of increasing temperature, or this the direction of increasing temperature on the x-axis, or the t-axis? The first one? Yeah.
I need to know what it is. Is it for water?
This substance is not for water, but I'm going to get to why it's not for water. But it's a subtle point. But a lot of substances have the same general shape. Most substances have this shape. Okay, so can you tell that this is the direction of increasing temperature? How about the direction of increasing pressure? Up. Okay. Now the direction of increasing specific volume. If you're like me, you have a lot of experience with temperature. Things are hot, high temperature. You have a lot of experience with pressure. High pressure, you understand that. What does it mean to have a high specific volume or a low specific volume? I'm still struggling with that. I'm still learning this topic, right? Because he's asked me, which way is high? Which way is low? Which one? Well, take two hands. This is the way I do it. And in my mind, I take two hands and I say, this is the volume for a trapped amount of mass. If the specific volume goes up, my hands come further apart, and there's more volume for the same amount of mass. So a large specific volume means I need more room for that same kilogram. I need more meter cubed for the same kilogram. Just like I have a good understanding of high temperature, and high pressure, I need to get a good understanding of specific volume. What does it mean to have a high specific volume? I need a large volume for the same amount of mass. True? So, which direction is for high specific volume? Is it this direction? Is that the direction of increasing specific volume? Or that direction? So the first one? Yeah, that's the right direction. Okay. Now, why don't they have one origin where these the corner of this plot where everything comes together, the three axes start and there's 0 temperature, 0 pressure, and 0 specific volume? Why don't they do that? Or did they do that? It's kind of tucked in the back, isn't it? Isn't it tucked way back there? I know I'm trying to show it, but isn't it in the corner that you can't really see? It's covered by the surface? Isn't that, well, hold it. It would be over here, wouldn't it? Not in the back corner. It would be low temperature, low specific volume, low pressure. Oops, put it right over here. There. Does that make sense? All right. So whenever you're confronted with a new plot or a new diagram, spend some time on the axes. Get to know which is direction of increasing, what are the typical units, etc. Let's continue to discuss this PVT surface. Find now on this PVT surface regions of single phase. Where is the solid only? Where is the liquid only? Where is the vapor only phases for this substance? Can you see that? So, how about this one? All of this region right here is solid only. That's the single phase region of the substance where it's solid. Well, tell me a little bit. What type of temperatures would you expect that substance to be in a solid phase? For low temperatures. Low temperatures. And what about the pressures? Whole host of range of pressures. And what about the volume? Do you expect a solid to have large values of specific volume? Actually, very small range of specific volume, and it's a low value. It's a solid. Okay, how about a region where it's vapor? That'll be this region out in here. Can you see that? Tell me about the temperature for the vapor. Higher. How about the specific volume? A lot higher than the solid. And what about the pressure? Lower, lower. You would expect vapors to exist high temperatures, low pressures, and have a large specific volume. What about the liquid? Right? So it's liquids have a range of temperatures up. They have what about the specific? What about the pressures? A whole range of pressures. What about the specific volume for liquids? Kind of a narrow range of specific volumes. And they're, as shown here, slightly greater than the solid. Isn't it? What's in common about the two single-phase regions, the solid and the liquid? If you just said geometrically, let me point out a distinguishing feature of these two regions. They're kind of steep. Aren't they steep? So think about it. As I want to make it the solid occupy a smaller volume, if I increase the pressure, does it dramatically change and make it occupy a smaller volume at the same temperature? Don't change temperature. Leave it at the same temperature. No, it's going to basically scoot up a very steep surface, meaning it's not going to reduce the specific volume much, but the pressure is going to go way up. You can increase the pressure of a solid without changing significantly the specific volume. Solids are fairly incompressible. Liquids. Are liquids pretty incompressible? Sure. Same thing. Fix the temperature. Think about the specific volume. Boost the pressure and see how much you can reduce the specific volume. No, it's just going to scoot up a very steep plot. In this diagram, where is the clear distinctive region between the liquid phase and the vapor phase? I can see that this is a nice boundary and a nice boundary for the vapor phase, but what's the boundary between the liquid and the vapor phase out in this region? There isn't one, and that's a critical point I hope you get out of this class. Okay, but what is a characteristic of a vapor out in this region compared to the liquid? Remember the steepness of the plot, the PVT surface? What about how steep is this? If I fix a temperature and I want to maybe boost the pressure, what's going to happen to the specific volume of a vapor? It's going to dramatically, it'll go down a lot more than the liquid or vapor, or the liquid or the solid. So guess what? Vapors are compressible compared to solids and liquids, which are essentially incompressible. We're going to spend more time on this diagram. So now that we have a region, understanding of axes, single-phase regions, let's talk about the two-phase regions. Where do I have a mixture of liquid and vapor on this PVT surface? The liquid-vapor mixture. It's in the dome. It's this shaded region, is it not? Is this it? Or does it go down and include all of this too? Is it truly just that shaded region? Is that the liquid vapor region mixture? How about this one? What is the solid vapor two-phase region? That's this one, like that, true? Isn't that it? And then the last one, what about the solid liquid two-phase region? That's this region right in here. So you can see that, let's say I have a solid. That's an easy one. It's at low temperature at intermediate pressure. There it is. There's the point. That's where I start. I start to heat it up by increasing the temperature, but not in changing the pressure. Leave the pressure alone. It's going to go along this surface until it hits a point. Then it's going to be changing to a liquid at the same pressure, and then come along this surface and it's liquid. Can you kind of see that? Following a path? So this would be going from solid to liquid at constant pressure on this PVT surface. It would go through this two-phase region where I'm changing phase. During the phase change, what happens to the specific volume? Does it increase from solid to liquid or decrease? It increases. So I'm taking solid and I'm turning it into liquid. That's melting. What's going to happen for the volume for that 1 kilogram of substance? If I'm melting it, the solid, what's it going to do? Is it going to go smaller volume or larger volume? Larger volume. That's what most substances do. That's what most substances do. What does water do? just the opposite of most substances. Water, let's do it this way. Maybe you think about freezing. You're liquid, you're cooling it. This one, it would occupy a smaller volume when it's a solid. But what would water do? What happens to water when it freezes? It expands. Why? Well, you got to go talk to your chemistry professor. Because the chemistry, they talk about the special nature of the water molecule. It's a hydrogen to oxygen. They have a very strong, what is that term? Dipole moment or something. They're very positive, negative. And so when they slow down in the liquid phase, they kind of line up feeling the positive, negative charge of the other water molecules. They get into a pattern which requires more space. They expand on freezing. It's incredible. Okay, how about this one? Let's take a solid or take a vapor or whatever you want to do. Which one do you want to do next? Let's take a liquid at constant pressure. And maybe it's right here at this pressure. It's liquid, and we're going to heat it up until it gets to this point. It's going at constant pressure, right? And then it's going to stay at that constant pressure until it goes from this liquid all the way out to vapor, and then it'll come out around on this surface at constant pressure. You're heating it at constant pressure. Do you see that path? So you went through this two-phase region of liquid to vapor. Okay, the last one, go at lower pressure in the solid, and then as you try to heat it up, you come up to be the solid, but as you try to heat it up some more at that low pressure, it'll change phase and then come out like that. So this is a solid to vapor phase transformation. They have the boundary of the two-phase regions are lines. You can see the lines. Those lines are saturation lines. So for the liquid, it goes here, liquid to vapor. That line is all what we call saturated liquid. And this line right here is all of the states on that surface which are saturated vapor. What about this word saturated? What's that mean? It's ready to do something very different if you bump it or try to change it a little bit. If you're at this point where you're saturated liquid, if you try to increase the temperature a little bit, you're going to get it to go into vapor. Or if you're saturated vapor, you try to decrease the temperature by cooling it a little bit, you're going to get liquid forming. So it's on the cusp of some phase change. That's what the word saturation means. Can you find the line of saturation lines between the solid and the vapor? It'd be right here and right here, isn't it? And what about between the solid and the liquid? Here for the solid to the liquid, this is a saturated liquid line. They're the edges of the two-phase region. How many people have saw this type of diagram before in their life? Yeah. So it's not the first time you've seen it, but we want to spend some time on it. Now, the big one is that liquid vapor dome. Why do we study so much this liquid vapor dome? Because it's a critical transformation in refrigeration and power cycles. Liquid vapor. And so this is what they would say is the dome. Why do they pick the name dome? If you look down this way, you see a dome. That's what you see, the dome. Okay. What's at the top of the dome? The one point that has the highest temperature at the top of the dome, that temperature is given a symbol T sub C. and it's called the critical point temperature. This point is the critical point, okay? What do you mean by critical point? I didn't make up the names. This is just the name used out throughout all the literature in thermodynamics. Oh, the critical point. Why didn't they call it some other name, you know? You could make up a name, right? Do you want to try and make up a name? The something point, okay? But it's called the critical point, and it's at the top of the dome. This point has a particular temperature, as well as, if you wanted to follow it back, a particular pressure for each substance. And that's the maximum temperature at which you can have a two-phase region, right? Let's do this. Let's say the pressure was greater than PC up here. Could I ever get it to be in a two-phase saturated liquid vapor mixture? No, you can't. Just like if the temperature is above the T critical, if the T is above T critical, could you ever get a two-phase mixture of liquid vapor? No, you can't. So this is the critical point, the top point. Now there's another line that's important. It's called the triple line. That one I can understand a little easier, triple line. Because we had single-phase regions, two-phase regions. Are there any three-phase regions? What do you mean by three-phase? Where the solid, the liquid, and the vapor can all coexist in equilibrium and be happy at the same temperature and the same pressure. Is there a place like that? It'll be a line. Where is that line on this diagram? Right there. Isn't that the line? So along this line, they call it the triple line, you can have three phases equilibrium. You can have vapor, liquid, and solid. That's kind of funny. Think about it. I have a container that's completely isolated from the rest of the world. Somehow I was able to control its temperature and pressure so that in the presence of gravity, the material is going to have solid chunk here, maybe a liquid substance covering it, and a vapor. And it's all the same substance. And that system is completely isolated from everything else. There's no heat transfer into it or out of it. And it'll sit there and it won't change phase. Some of the liquid won't go to solid or to vapor. It'll just happily coexist. This class is remarkable, isn't it? Think about that. But it's only at a particular temperature and a particular pressure that this can work for that substance. All right. Professor, somebody else drew a diagram and they went like this with the same concept, and they put the vapor on top because in the presence of gravity we know the vapor is going to be lighter and it's going to, go to the top of the container. And then they put the liquid right like this, liquid, but they put the solid kind of floating in the liquid. Not you drew it to the bottom of the container in the liquid, sinking in the liquid. Which way is it going to go, Professor? It could be either way. For this diagram, as shown, the critical observation is right here. What about the change in the specific volume when you're going between that liquid and solid? Liquid and solid. Can you tell whether or not the solid's going to float in the liquid or is it going to sink in the liquid? Going to sink. Because the lower, this is the specific volume of the solid, it's lower than the specific volume of the liquid. You can see that. And the reciprocal is the mass density, but I'm trying to get a good grasp on the specific volume, so I use my hands. A lower value means it's more dense. It's occupied for the same amount of mass that's occupying a smaller volume of space in the solid phase, hence it's more dense, it's going to sink. But what will ice do? What will water do? Your experiences, every time you have a beverage, you have ice cubes in your water, they float. You may have never seen an iceberg, but in pictures, you studied icebergs, floats. And so the solid chunk of water known as ice will float in the liquid water.
Is there an example where you have all three of those, like in the real world?
Sure. And we'll tell why they benchmark to it. Yes. Here's a question. Is it possible to have a pure substance being 1/3 by mass liquid, 1/3 by mass vapor, 1/3 by mass solid, all in equilibrium? Yes or no? Yes, that's what we just talked about. And it's not going to be at any pressure and any temperature. It's going to be for that substance only at this particular temperature. That temperature is not the critical point temperature. That's the triple point temperature. And only at that pressure, which is not the critical point pressure, but the triple point or triple line temperature, triple point or some subscripts for that unique temperature and unique pressure. How about another question? Is it possible to have a two-phase mixture of liquid, vapor, water in equilibrium with temperature above the critical point temperature? No. No. Look at that dome. As soon as your temperature, there's something very interesting. And when we get to the table, students will be in this table and they'll be like, I can't find it. I can't find it. Well, what do you got? They got something at a temperature well above the critical point temperature, and they're looking in the two-phase region for it. You know, it's like, it's not going to be there. So the answer is no. How about this one? Is it possible to have pure liquid water in equilibrium below, at a temperature below the triple point temperature? You got to go back and look at that diagram. First, understand the question. We're going to ask if we can have water, liquid water, at a temperature below the triple point temperature. Can I have liquid water? Okay, we got the question right in our mind. We go back, and I know that this is not the diagram for water, but it's the same trend. Can you see it? Can you have liquid water below the triple point? No, you cannot. If you can make these type of observations and remember these things, it'll do you well as you struggle with looking up properties. What is a characteristic of the nearly incompressible phase on PVT surface? Somebody says, we can treat it as incompressible. What does that look like on a PVT surface? Steep. That's the word I'm looking for, steep. So we see that these regions are very steep for the liquid and the solid. The one that's compressible, the vapor, not so steep. I forgot to point out on this diagram, it's very important that you have this shaded region is always, not always, but it's very often shaded. Why? Because we focus on that region. But, when they have a region that's shaded, that's pulling your attention to it, true? Is there any other regions on this plot that are shaded? Yeah. Okay, let's identify them. What's this region? Why did they shade it? It's a cut. They had to stop and put a border to the plot somewhere. But it's not a single phase or a two-phase or a three-phase region. It's not where you can have a substance actually. It's not part of the surface. It's just a truncation of the plot. Why did they shade it? I don't know. And if I was the editor, I'd tell them to take the shading off. Okay, what about this triangular shaded region in here? It's just a slice where they stop the plot. Okay? sometimes you get confused. The student thinks, well, this looks like everything below that surface is what's of interest. But it's a surface. It's not a volume plot. All right. How about this up here? They could have shaded that, but they didn't shade it. And I'm glad they didn't, because it's just they had to stop the plot at some high pressure. All right. Here is for water, H2O. Here is for all other substances. What is the difference between the PBT surfaces? It's that solid liquid change. And from your experience, you know that if I'm in the liquid phase and I'm cooling water, I'm going to hit this and it's going to be saturated liquid. And if I try to make it go into the solid, it's going to come back around. See how it's coming back around? It's hard to show that in 3D from this angle. But it's going to come back around, meaning there's an expansion when it turns to solid. It's less dense. It's going to float in the liquid. It's what you know. The other something, too, that's a little unique is this surface, if I look at the way it's inclined with temperature, doesn't it kind of lean back with temperature? See that? This two-phase region with the solid liquid, which way does it lean with respect to temperature? It leans that way, doesn't it? Can you see that? That'll be a subtle point when we look at projections of this surface. So what we want to do now is 3D is great. But 2D is a lot more understandable. So we look at two-dimensional projections of the surface. So if I take a look and I say I want to plot the PT diagram, two-dimensional projection of that surface, what do? Well, I want to plot this axis, pressure going up, this axis, temperature. So I don't look with my eye that way. I don't look with my eye that way, but I look with my eye that way. When I look with my eye that way, temperature axis, I see it fully, and the pressure axis, I see it fully. So the projection doesn't see the specific volume. You're looking down the specific volume axis. See that? And so that's a projection. If you look at the projection here, this is what it looks like for water. What does the triple line look like? It looks like a triple point. So sometimes I'll say triple point. Sometimes I'll say triple line, but it's for the same meaning because it's a projection on the PT. This is a very, very common plot, the PT diagram. And then I say, can you see the vapor region? Sure. It's everything. How about the critical point? Looks like a point. How about the liquid region? Sure. How about the solid region? Sure. What about the two-phase regions? Well, this dome projected to a single line right in here, didn't it? If I can encourage you to spend some time on the PT diagram, I would strongly do it because I have taught Thermo 1 many times, Thermo 2 many times, and a lot of times it's like, okay, to answer your question, let's redraw the PT diagram. And now let's just get oriented and ask you a few questions. Usually if I can get the student to answer the questions that I ask them about the PT diagram, they'll answer their own question eventually. So the PT, how many people remember? You've seen this in another class. I know you have. Chemistry, maybe physics. Okay, so this is a solid. So this is a two-phase region. It's a line, two-phase region, a line, and a two-phase region, a line. What's happening when I go from, let's say, this point, liquid to vapor? What do you call that? Liquid to vapor, phase change. Liquid, evaporation. Vapor to liquid, I'm going that way across the line. Condensation. Let's do solid to liquid. Melt. Liquid to solid. Freezing. And then the harder ones, right? The solid to vapor, sublimation. The one that's vapor to solid, some sort of deposition. Yes?
Can we assume that the triple point is basically the triple line and you basically condensing it?
That's it.
Pinching it together?
Yeah, you look down a line and it's aligned with the axis and all you see is a dot, a point. That's right. Now the critical point truly is a point, but you talk about either the triple point or the triple line. Now we're going to talk about a PV. Well, what's the projection? Which view do I take of this PVT surface to get a PV diagram? Do I look this way? No. That gave me the pressure temperature. Do I look this way? No. Do I look this way? Yes. Yes. And when we look that way, it gets pretty complicated, but we actually see the dome pretty well, don't we? And we see the critical point at the top of the dome, and we see the line for the triple line. All right. Now, they're trying to show you the solid vapor and the solid region and the liquid region, and it gets a little cumbersome because they have to introduce a dash line. Why do they put a dash line there? Because you're looking this way, and it's in that phase change, it wraps around, so you're trying to get the surface behind. Okay? So that projection. So a lot of times when they plot a PV, they'll just show the dome. They'll ignore all about the solid and liquid region, and they'll ignore down here. And they'll usually just plot, maybe if I can show it, something like this. Let's just focus on this region. Above the pressure of the triple point pressure, and that way I ignore the complexities all in here. Okay. Here is a PV diagram for water, and just what I said, they tried to ignore the vapor region below and pick it out. But can you see what do we have here? Now this is a temperature. This is a temperature-specific volume. That's a typo, right? Temperature-specific diagram for water. Let's go back and look at it. Which direction do you look at for the temperature-specific volume? From the top. Look down. But it's a very similar shape. You see that dome nice and clean, don't you? So the temperature-specific volume plot. Now, this is always interesting. When you're looking down, you can see the liquid region, the two-phase liquid-vapor mixture region, and the vapor region. You see the critical point? They sometimes don't draw the triple line on it, but there's a line. Typically, you're not interested in how cold it is. And what are they showing you with the line that's labeled 10 megapascal? What is that? Line of constant pressure. So you could play the game of starting way out here and say, oh, I'm at this temperature above the critical point temperature. I'm at 10 megapascal. I'm out in the superheated vapor region. But then at constant pressure, I cool it. I'm lowering the temperature. It's going to get to this point. It's vapor. But if I try to cool it anymore, what's going to happen to the vapor? I'm going to start condensing it. And right now, it's 100% vapor. But when I get to this point over here, what is it? It's not 100% vapor, it's 100% liquid. How about if I stop cooling it right in the middle? I may have a mixture of 50% by mass vapor and 50% by mass liquid. A two-phase mixture. Then if I cool it some more, the temperature is going to drop, and I have colder and colder liquid. All of it is always at 10 megapascal. That's a line of constant pressure. You could put a line of constant pressure at lower pressure or a higher pressure, or even up to 30 megapascal. See what they're showing you? They're plotting lines of constant pressure on a temperature volume diagram. there's some very interesting things. Take a look at this value of specific volume when it's 100% vapor at 10 megapascal. And for the same pressure, this is the value of specific volume, okay? And it's 100% liquid. Well, they talk about it being saturated liquid and saturated vapor at that pressure. Well, the subscripts get long, so they abbreviate the subscript. And can you see what they use for a subscript when it's saturated liquid? F. Can you see what they use for a subscript when it's saturated vapor? G. This is always confusing to students. It's like why G and why F? The G is a little easier. Gas. Why F? It's not really for fluid. It goes back to a lot of the thermodynamics was done in Europe. A lot of Europeans contributed. You'll see a lot of European names or German names that contributed. And what is the German word for liquid? There it is. And what's the first letter of the German name for liquid? F. And so a lot of the German tables had subscripts F for it. The other thing is well, if you put in vapor, you're not going to get probably maybe you get some. I didn't do that for G. But why didn't they just say, well, we're English, let's put L there. L for liquid, that would make sense. G for gas, L for liquid. Well, we don't have, especially when they did this work a long time ago, they didn't have very sophisticated font selection and all sorts of footnotes and clarity and everything, and it was easy to get confused because you may write V sub 1 and then you may write V sub L, and L looks a lot like 1. And still today in a lot of journals and stuff, they say, do not use the subscript L. It's just a rule. Why do they not use the subscript L? Because it can be easily confused to a reader, and so they want to avoid it. So that's two reasons why we still have F as a subscript for saturated liquid state. Well, I'm going to plot that plot again, but I'm going to do it true to life, because what we do often is we put up these cartoon type plots of data, but they're not true to life. They're not real data being plotted. They're to give you an illustration. So this is being done with some software. You can get a student version of this, download it to your PC. All you have to do is type in student version of RefProp. It's done by the NIST, National Institute of Standards and Technology. If you want the commercial version, it costs a couple $100. It's a bargain, but students can get it limited properties for free. So I can get that, and this is what I did was I plotted in that software, RefProp, the temperature volume diagram for water. And instead of just kind of cartooning in, I said, no, let's plot it for this 0.104 megapascal, which is, did I put a 1 in there? I may have typed it wrong. But it comes in right at 1 bar, okay, close to atmospheric pressure, and the boiling point is 100 degrees C, and that's what it looks like. Here is a line of the 1 megapascal. They didn't have it here, but the 10 megapascal, they showed that line. Then they showed a line with a particular pressure of 22.09 megapascal. That's the critical point pressure for steam. 22.09 megapascal. So that line comes down and it hits right through the critical point, then it skirts down. But you could see I plotted it in red. And then the last one is the 30 megapascal line. This is data true to the units and everything plotted in RefProp. But what did they have to do on the x-axis to make that plot work? What's the difference between the y-axis data and the x-axis data? One is log and one is not log. Is this a log-log plot, a semi-log plot? This is a semi-log plot. Why did they put the specific volume in log? Otherwise it'd be super long. And that's one of the things when you see somebody writing this cartoon, that really kicks out very far, this side. And what about over here? It is super steep. It's super steep. Okay, so these diagrams, I know we show them, but even on a log scale, they're super steep and they kick way out on the edge. So what does that say? If I have a modest pressure and I'm changing phase, I have a dramatic increase in the volume. 1 kilogram of liquid goes to a bunch of, 1 cubic meter of a liquid goes to many cubic meters of a vapor at the same pressure when I boil it. And that's really the secret of power plants. That's why they work so well. Is you're expanding the working fluid. Now you have a lot of volume. You can throw it through the steam turbine and make the turbine generate a lot of power. The triple line looks like a point on what projection of the PVT surface? The triple point looks like what projection? The line looks like a point on what projection? PT? Right? All right. The two-phase liquid vapor region looks like a dome on what projection? The two-phase liquid vapor region looks like a dome on what projection? Does it look like it on a PV? Yes or no? Yes. How about on a PT? No. How about on a TV? Yes. So this one was a trick question. It had 2 right answers, right? All right. How about the next one? The two-phase solid vapor region. Hold it. Did they say solid liquid or solid vapor? Which one? Solid vapor. Okay. Now I've got to think. It's not the shaded solid liquid. It's the solid vapor. Where's that one at? Is that down in this region? Yeah, okay. What does it look like on a PT projection of the PVT surface? Line. And I know I'm going fast, but please struggle with it, and it'll reap great dividends. This is a classic thing that most engineering textbooks spend some time on and really beat to death. And it may seem like I'm going to spend a few minutes on this. It's wasting your time. It's not. It's really not. Get this down and you'll go a long way in thermodynamics. So we take a trapped amount of mass. Let's start with 1 kilogram. Let's do it with our favorite substance, water. 1 kilogram of water, W-A-T-E-R. It's H2O. We put it into a piston cylinder apparatus such that the weight of all these pistons maintain 1 atm pressure. It's not a mixture of air and water. It's pure water. It's always going to be maintained at 1 atmosphere of pressure. And we start at this temperature. Tell me a little bit about negative 40 degrees C. Hot, cold, what do you think? Super cold, really cold. What do you think about water, 1 kilogram of water at that pressure and temperature? Solid. Solid. It's ice. It's a chunk of ice. But somehow I got a chunk of ice and I have it in this piston cylinder apparatus. And what do I do right here? I heat it up. I have a little heat source. So what we're going to do is we're going to plot the amount of heat added in kilojoules, or you could put kilojoule per kilogram because we just have 1 kilogram of mass, but kilojoules makes more sense. How much heat is added, and we're going to watch the temperature of this chunk because this is a thermometer, and we're going to monitor the temperature. So let's go ahead and think about what type of units I want to put in for each of these, and I'll try and draw it a little bit closer to scale. So let's say I want to go to, I don't know, let's do 3,000. 0, 1,000, 2,000, 3,000. Here's even 4,000. Extend the axis. All right. What about the temperature? Well, we're starting at negative 40, and maybe we'll go up to 300 Kelvin, or not Kelvin, degrees C. So maybe I put 0. This is negative, 100. This is 100, 200, 300. Okay? I start, and I haven't added any heat yet, and the temperature's at negative 40. Where is the first dot on this plot? Where is the starting point on this plot? It'll be right around this point, negative 40. And I haven't added any heat yet. But now I start to add kilojoules of heat. I'm adding the Q. What happens to the temperature as I start adding? It's going to go up. It's going to go up. So something special is going to happen when I hit 0 degrees C. Do you recognize that as a special number for water? What happens with water 0 degrees C? Phase change. So I'm coming at it from a solid. But then I'm going to hit 0 degrees C, and what's going to happen? It's going to start to melt. So let's do this. I've got to, first of all, put on my glasses so I can see. I got some numbers here so we can draw it to scale. And what we do is if we put in around 78, around 80, where's 80 out of 1,000? Well, it's way down here. 80. It'll come up and it'll hit 0 degrees. All I have to do is add 80 or 78 if you want exact. Okay, let's try and do it exact. 78.3, too many digits. Kilojoules, I will have taken the solid ice from negative 40 to 0 degrees C. But I'm going to have to add not just 78, I'm going to have to add 333 kilojoules to go from saturated solid to saturated liquid. So if I add that, I need to come out to about 412. And what's happening in this region? You're going from saturated solid to saturated liquid. It doesn't change the temperature. The temperature completely stays the same. I can ask this question of students in Thermo 2. I can ask this question of students in heat transfer. I can ask this question of graduates or anybody, and half the time they'll miss it. Can I add heat into a system and not change the temperature of the system? Yes or no? This is it. This is a good example of it. And yet some people go, hold it. You mean you're going to transfer heat into the system, into the fluid or substance, and the temperature of the substance won't change? Impossible. No. This is a big deal. Because we're doing it at constant pressure, it will stay at that temperature until all of it goes from saturated solid to saturated liquid. It's a phase change. That's how we do it. So this big number is, it takes 333 kilojoules of heat coming in to have a change of phase from saturated solid to saturated liquid. Now we continue the process. If we add more heat above the 412, what's going to happen to the liquid? Temperature is going to go up. That's exactly right. So the temperature is going to go up. Because it's always at 1 atm, it's going to go up until it hits another very special temperature for water, not 0 degrees C, not the freezing point, but 100 degrees C, which is the boiling point, right? So how much are we going to have to add? Where are we going to have to go? Well, you only have to go up to about 831. And it'll be up here like that. Like that. It'll hit 100 degrees C. This point, it's also saturated liquid. Isn't it always liquid between 0 and 100 degrees C? But it's saturated liquid at the beginning at 0 degrees C, meaning if I cool it, I start to get ice. But it's at 100 degrees C, if I heat it, that saturated liquid, some of it turns into vapor. Does that make sense? It's like I can call this saturated liquid and I can call this saturated liquid. One's at 0 degrees C, one's at 100 degrees C, one's at the cusp of making ice, one's at the cusp of making vapor. Okay, so now if we then start adding more heat to the saturated liquid, it stays 100 degrees C and we march off, increasing amount of Q needs to be added. The temperature stays the same until we get from 831 all the way out to, believe it or not, around 3080. That amount of heat to be added for 1 kilogram of water to change it from saturated liquid to saturated vapor is 2,260 kilojoules. It was only 333 to change phase from solid to liquid, but a bunch more, 2,260, I'm rounding off a little bit, to go liquid to vapor. Now once it's out here, this is saturated vapor, isn't it? Once it's saturated vapor, can I still pump in some heat? What will happen to the temperature? It'll go up. The temperature will go up. Let's say I want to take it up to 200 degrees C. How much heat do I have to add? Around 3,290. 3,290. So it'll be up to 200. And then what happens if I wanted to get it up to 400 degrees C, or no, 300? I didn't do it. I didn't do anyway. It just goes up like that. I have it for 400. At 400, it's 3690. It's around 3690 there, like that. If you want to look at the data that I used to plot this, I'm going to show it right here. You should be able to reproduce this out of our table in the textbook appendices. I put in extra information about specific volume, the reciprocal specific volume mass density, the internal energy. The key one is the enthalpy, which I haven't explained. The Qn is the changing of the enthalpy. This is specifically the latent amount of heat, meaning it's like I'm putting in heat, but I don't realize a change in temperature. They call that the latent heat. That's old terminology. It's still out there. They have the sensible heat. Well, if I put in heat, then I see a temperature rise. That's sensible. Latent, I put in heat, it's hidden. Where did the temperature rise go? There's no, something's hidden, latent. That's the term. They say, why is thermodynamics so hard for students? Half of it's the terminology, isn't it? So this is the amount for the what we call HFG, going from saturated liquid to saturated vapor. This is heat, not of vaporization, but the heat of solidification or melting, going from solid to liquid. And we're going to talk about specific heats if you like, and the volume expansion if you like. Let me back up. I wanted to talk about a lot more, but what is, you all are familiar with specific heats, true? C sub P. Or a lot of times you neglect the P, but this is all done at constant pressure. Constant pressure. So let's put a P on that, a subscript on that specific heat. What is the definition of the specific heat from your memory? Yeah, so I'm going to show you one definition. It's the rate of change of enthalpy with respect to temperature, or it's how much heat comes in, and then you realize amount of temperature change. So here, you have a slope of a line, right? The slope. But the specific heat, because of the axes, it's 1 over the specific heat. It's a reciprocal. The slope of this line would be what is the rise, the temperature change. So the slope is rise over run. Does everybody rise over run? Remember that? And then this rise is a temperature change over the run, how much heat was brought in, Q. But if you reciprocate that, you get the specific heat. So on this plot, we can talk about the specific heat of water in the solid phase. And that specific heat of water in the solid phase is around 2 kilojoules per kilogram Kelvin. Okay. We could talk about the specific heat of water in the liquid phase. It's around 4.2 kilojoules per kilogram Kelvin. And we can talk about the specific heat, 1 over C. C is around the same 2 kilojoules per kilogram Kelvin out in the vapor phase. If you want to take a look at those numbers again, here they are. Let me pull this down. The specific heat's around 2 in the solid phase, around 4.2 in the liquid phase, and around 2 in the vapor phase. Okay. So there's the specific heat information. And then one other thing that I have right here, which is of interest, it may be overloading you. I'm sorry if it's overloading you, but it's the volume expansion. You have a chunk of 1 kilogram of water. It's solid. You start heating it. It really doesn't expand much going from negative 40 up to 0 degrees. Do you see that? It expanded by what? Less than 1%. But when it went from saturated solid to saturated liquid, did it expand on melting? No. It contracted. So it actually is negative 8%. It takes less volume, the liquid does. But that's a pretty big change of volume, 8% on the melting. But then as I heated up the liquid, it expanded a little bit. But look at this. I couldn't even put it as a percent. Look at the volume expansion. It went up 1,600 times, almost 2,000 times. So if I had 1 little liter of liquid water, I put it into a boiler, I got almost 2,000 of those coming out. That's a lot of volume to push through a turbine to make energy in a steam power plant. So many students will pass thermodynamics and they won't be able to explain how a steam turbine power plant works. and it always bothers me, and I'm trying right now to explain something really important. You got a lot of volume coming out, and it's able to push and expand through a steam turbine. This is incredible. 1,600 times. How many people would love a bank? I go in one day, I give them $1 deposit, come back a week later, they give me $1,600. That's like what's going on in the boiler. This is great. I'm going to take $10 next week. And then next week, I'm going to take $100 into that bank and get that return on the investment. That's the type of return we're getting. Now, you still have a modest increase once it's superheated. You're still expanding it, but not dramatic. This is the one I really wanted to point out. You have a huge increase in the volume of water when you change phase from liquid to vapor. All right, we're done with that. Do you have any comments on this? Questions or anything?
For
Yes.
the 2000, that was from 100 to 100 degrees? Or what was it? What was the change in temperature for that?
Oh, I'm looking at the V sub F to V sub G, the change in the volume, and that's 1,600. The volume expansion.
What temperature is it?
100 degrees. 100 degrees C. Yes.
Was that 1,600 like 1,600%?
No, I got rid of the percent. So it's just, the rest of them I put as percent so I could see them better. They're smaller. But yes, that's right. I had it as a percent. It didn't make any sense. It was so huge.
Will we ever solve for volume expansion?
Oh, we're going to do a lot with that. We're going to do a lot with all of these properties. Specific volume, temperature, pressure, internal energy, enthalpy, yes. Yeah, but I'm afraid that somehow we don't emphasize why or how that power plant works like that. There's a couple other things I'm going to hammer to hopefully when you pass the class you will know, because I've seen students, they pass the class and they forget all about thermo, and somebody asks them a question and they have a wrong concept. So hopefully this helps you a lot. Think about it. It takes a lot of energy to boil water, but there's a lot of volume expansion in it. And now I have a lot of volume to push through a turbine. It doesn't take that much. It's not like this is 1-to-1. The amount of energy to change phase from liquid to solid is a small amount compared to the vapor to liquid. Okay. Quality. This term is confusing. This term is given the symbol X, thankfully. It's universally known. And it's used when you have a two-phase mixture of liquid and vapor. And what it is a mass fraction. So that's by definition the amount of mass that's in the vapor phase divided by the total amount of mass that's in the liquid vapor mixture. Well, the mass that's total is either going to be in the liquid phase or the vapor phase. And so this is another way of writing the term quality. Quality is simply a mass fraction. What is a common mistake? They'll say quality is a volume fraction, volume vapor divided by the volume total. This is not right. No, no, no. It's mass. Think about this. I have a mixture, and if I wait long enough in the presence of gravity, the liquid will settle to the bottom and the vapor will be at the top. But most of the time it's running through a pipe and it's well mixed. Okay, but what we have is we would say, I want you to calculate the quality in this system. You would just do the mass ratio. Okay? Okay. Internal energy. Well, that was a property we were introduced to the previous chapter. We had cap U as well as lowercase u. What were the SI units on cap U? That's kilojoule. How about lowercase? Well, it's cap U divided by M, SI units of kilojoule per kilogram. Internal energy, specific internal energy. This property you can now get, and I'm going to show you how to get it out of the tables as a function of temperature and pressure, as well as other two independent intensive properties. Fix the state, allow you to get the other ones. Enthalpy. Enthalpy is a new property. Here's its definition. Just accept it. I will beat up why it's a good definition. It's U plus PV. All right. The cap U means something special, just like the cap H means something special. It's the total enthalpy, the total internal energy. You can divide this whole equation by mass, and you'll get lowercase h, lowercase u, lowercase v. So you could put it on a specific basis, specific enthalpy. SI units, kilojoules per kilogram. This one, kilojoules. Professor, you just defined it as that. Why did you define it as that? We'll see that it's very useful. But at this point, it's simply a definition. So it's a new property in terms of old properties or properties you're already familiar with. So this whole part now is about retrieving properties out of the tables. So we're going to emphasize SI units. They have a whole set of tables with BTUs and pounds and that. But this is a long table. How many parts of this appendix? How many tables in this appendix? A lot. Just got to go one step at a time. Let's take a look at table A1, then A2. Table A1, you probably already spent some time in it. So they list the substances. They give a chemical formula. What do they give you here? The molar mass. The molar mass. What do they give you here? TC. Maybe before this lecture you didn't know what TC meant. But now you do, and I heard a number of students already say it. It's the critical temperature. Is that the temperature along a line or a temperature at the top of a dome? Top of a dome. How about PC? Critical pressure. And ZC is a ratio of the critical pressure, the specific volume at the critical point, the R, the gas constant, and TC. And it's just computed and compiled. Is if this number was close to 1, it would act like an ideal gas near the critical point. But it's not close to 1. Guess what? It doesn't behave as an ideal gas. Vapor, close to the critical point, does not behave as an ideal gas because you can just see it's not close to 1 at all. But that's what ZC is. Don't worry too much about the definition of ZC. It's a compressibility factor at the critical point, but just the computation of it. Okay. Let's take a look here. What is argon? It floats around as monoatomic. Argon. Its molar mass, its critical temperature, and critical pressure. What do you think about the critical point temperature for argon? Is that hot or cold? Very cold, right? That's 151 Kelvin. Subtract off 273, you're going to have large negative degrees C for how the temperature. So you can get argon to condense, but you're going to have to get it really, really cold before it condenses. There's other things, butane, benzene. This table goes on. Let's jump on. Here's table A2. Already it seems like we're overwhelmed. But look at the title of it. It's the properties of saturated water, liquid vapor, and it's a temperature table. The main input is that first column. And what is in that first column? The temperature. So if I'm looking for properties for water, and I think it's in the liquid vapor region at 10 degrees C, here's a whole host of numeric values of properties. Notice they put 10 over here again. Why did they put 10 over here again? To help you stay on the right line and avoid a common mistake of wandering over and dropping or going up in a line, right? So try to, that's why they put it there. Try to avoid that mistake right away. So what about this? pressure. That's the saturation pressure at that temperature. Psat at that temperature. Remember our pressure temperature diagram. Remember going from the triple point to the critical point, there was a whole host of states from the triple point to the critical point where you went from liquid to vapor. But there's only one pressure for each and every temperature. That's the saturation pressure as a function of temperature. So if I wanted to know the saturation pressure for 6 degrees C water, there it is, in bar. If I wanted to know it at 100 degrees C, there it is, in bar. If I wanted to know it at 360, there it is, in bar. Make sense? All right. Couple points. This line is very special. What's special about 100 degrees C? Boiling point of atmospheric pressure. Guess what pressure this is? The saturation pressure of water at 100 degrees C is atmospheric pressure. Yeah. So this is all of these, that's what they're giving you from the triple point up to the critical point. Maybe I should have emphasized that. What is the lowest temperature put in table A2? 0.01. That's the triple point temperature. That's the lowest temperature. And there's the pressure for it. Talk about that pressure for a minute. Pretty low, isn't it? It's very low. Actually, if I had a container of water at the triple point pressure inside, it would be at a state of vacuum with the surroundings outside. If I took a ice pick and popped a hole in the container, I like to ask this question a lot. I'll probably ask it a lot again over the semester, is what's going to happen? Is the steam inside going to rush out? Or is the air going to rush into the hole, into the container? Air's going to rush in. Yes?
Sure, I was doing examples on the chapter, and like they would say compare specific volume 1, specific volume 2, specific volume 3, and one of them was times 10 to negative third, but none of my tables have times 10 to negative third. I was wondering if there was a typo in the appendix.
I don't think there's a typo in these appendices, but let me look at it later for a typo. But let me do that because I need to talk about that exponent in this table. I need to. But before I do that, let me continue to go. This table goes on multiple pages. This is the first entry, and we understand that that's the triple point. The last entry, when you see something the 4 and 5 significant digits, that raises a red flag, something special. So what's the highest temperature? It's 374 degrees C, right? And there's that corresponding pressure. What is that point called? Critical point. You can't have a two-phase. Remember, this is always liquid vapor, two-phase, saturated water table. You can't have liquid vapor mixture above that. So it goes from this temperature to that temperature. Okay. Now, the first set is a specific volume in units of meter cubed per kilogram, and they give us two columns for the specific volume. Saturated liquid, saturated vapor. What subscript do they have on this V? Subscript G for saturated vapor. What's the subscript on the saturated liquid? F. Goes back to that German word for liquid. Okay. Now, somebody says, I want you to give me the saturated vapor, V sub G, at 10 degrees C. You would look over, you'd grab that, and you'd say it's 106.379 meter cubed per kilogram. This is the one that gets students. Somebody says, okay, I want you to read for me, and everybody, I want you to do this right now. I want you to give me V sub F at 10 degrees C. So many meter cubed per kilogram. I'm going to pause. So the answer that I'm looking for is 0.00010004. You could forget the .000. And now if I just said, give me one or two significant digits to that number, you'd say it's 0.001 meter cubed per kilogram. 1 kilogram of liquid water doesn't need much space. How much space does it need? 1,000th of a cubic meter. What is 1,000th of a cubic meter? How many people ever bought gasoline by the liter? Anybody buy gasoline by the liter? Yeah. How many people purchase beverages in the store by the liter? 1 liter water bottle, 1 kilogram. You've got a good visual image of the volume and the mass inside. And you're saying, Professor, I don't think my water is saturated liquid that I'm drinking. Yeah, I know. It's lower than the temperature than a boiling point. You're not drinking at 100 degrees C, are you? No. But density of liquid water doesn't change much with temperature, does it? Nor with pressure. Remember the steepness on the PVT surface? Okay. So this is the critical point. That's the triple point. In between, you can have a two-phase mixture. The common error is how to handle this 10 to the 3. And some of you said, oh, it's 1,000, meters cubed per kilogram. No, it's not. For V sub F, it's 0.001. So you divide by that 10 to the 3. If you want, there's not too much of a tricky header. It's only on a specific volume you have this 10 to the 3. There's no 10 to the 3 over here or anything. Here's our saturated liquid, saturated vapor, internal energies, saturated liquid, saturated vapor, enthalpies. But what do they give here? HFG. All they did was they say it's so common to take the difference between H of G and H of F that we're just going to do the difference and we'll add it as an extra column. That's the heat of vaporization. Remember at 100 degrees C, around 1 atm, how much energy is required to change phase from liquid to vapor? 2,260 roughly. 2,260 kilojoules to change 1 kilogram from saturated liquid to saturated vapor. What does it take at the critical point to change from saturated liquid to saturated vapor? Professor, I think there's a typo. That number's 0. Is it a typo? It's where they come together and we lose the distinction between what's a liquid and what's a vapor. When you get above the critical point, let me jump back here. Okay. Well, you could do it on this diagram. What do you call this fluid up in this region? Do you call it a liquid or do you call it a vapor? Where's the demarcation? They're arguing always about where's the boundary between this state and that state? Where's the boundary between this country and that country? Where's the boundary between my land and your land, or my neighbor's land, right? Where's the boundary between liquid and vapor on this diagram at temperatures above the critical point temperature? There isn't cleanly defined. They just call this supercritical. Supercritical steam. We're going to have our power plant running in the supercritical region. Sure, you can, and a lot of plants do. Okay. So, you lose the distinction between saturated liquid and saturated vapor in that HFG. Look at the H of F and the H of G. Aren't they the same value at the... Yeah, they are. Table. Oh, I had questions. Let's see if I can uncover these questions. What is V sub F at 100 degrees C? Which one's correct? B. And what is the triple point pressure? This one takes time. how many units of pressure are there and how often are they misconstrued and made an error on? What did the author do right here? On each of these tables, he puts the same little reminder that if you want to convert these units, now in the previous edition, I don't know, he did it, last couple editions he did it. He said 1 bar is 0.1 megapascal. 1 bar is equal to, what is that, 10 to the 2? Yeah, 10 to the 2 kilopascal, right? So you can go from bar to megapascal and bar to kilopascal. You don't need that helpful reminder, but there it is. So, what is this number? It's 6.11 millibar. They give it to you in bar. If you go 1, 2, 3, is it 6.11 millibar? Yeah, that's okay. How about 0.00611 kilopascal? Is that okay? No. How about 611 kilopascal? It won't work, right? That won't work. And then 0.0611 megapascal? No, the only good answer is the A. But be very careful on your pressure conversions. Okay. Reference state, last slide. Take a look at this table, and you have to pick a starting point. The starting point in the steam tables is just an arbitrary reference point. Now, there's a lot of consensus out there in the literature about what it should be, but it's not uncommon for a student to get a table out of one website and a table off another website, do the calculations, and get crazy answers because they have different reference points. You've got to be very careful about reference points. But for water, take a look. We're interested always in changes in energy. Where is the beginning of the energy measurements that are eventually just going to cancel out because we're always looking for a change in the energy? That's what's most important. For water, where is our beginning point for energy measurements? It's somewhere on this table staring you in the face. Where is it at? Well, we'll start at 0 and measure up. Where did they pick to start measuring energy? This is volume. This is entropy. These are my two energy. One is called the internal energy. One is a term that you're less familiar with that's called the enthalpy. There's 0. They picked that saturated liquid at what point? The triple point. That the internal energy of saturated liquid at the triple point will be picked to be 0. That's our starting point. Can you get water to be at a lower temperature than 0 degrees C? Could you get it at negative 20 degrees C or something? Sure, I would expect it to be solid. Guess what? If you look for U, the value of internal energy, at negative something, guess what you're going to find that value of U to be? Negative. It'll be negative. Meaning that from that reference point, you're going to have a lower, so it's a negative internal energy at that lower temperatures. All right, I'm going to go ahead and stop there.